All right, welcome class to lecture 20. We have over the last few lectures moved away from linear response and begun thinking about nonlinear phenomena. We started that discussion with a little vignette on really far from equilibrium behaviors where much work is left to be done. And we're going to turn our attention to now a very, in some sense, far from a very non-equilibrium phenomena that associated with the statistical mechanics of democracies or social sciences. Just kidding, April Fools. No, rather we're going to think about something that is much more at home in the chemistry department for which this class is being taught. And we're going to start thinking about reactive rates and rare events. The fluctuations fundamentally dynamical in origin, which will admit the breaking of bonds, the transformation of one phase to another. We're going to work towards a theory by the end of this lecture that we can use to actually estimate the time it takes for one of those processes to occur. The results will look familiar. It'll be something whose form you have seen before, but likely it's not something that you knew had strong theoretical underpinnings. So that basic theory will be laid out today. We will approximate it in a specific, in a very straightforward manner in this lecture. And over the next couple lectures, we will learn how to relax that approximation, account for interesting dynamical events that occur as a reactant transfers to a product. And in a final lecture on this topic, apply it to a reaction of kind of fundamental interest, namely how an electron moves from a donor to an acceptor, bringing in some quantum mechanical details in the process. So to get everyone on the same page, what we envision trying to understand is if we had a free energy surface, say W of Q, where Q is some reaction coordinate, something that distinguishes a set of reactants, call them A, from a set of products, call them B. And by distinguish, I mean that there are features on that free energy surface which mean that A and B are long-lived. Namely, there exists a barrier, say at Q star, that separates basin A from basin B. That means to go from basin A, which over the course of thermal fluctuations, the system will explore that basin. But to get to basin B would require a rare fluctuation that localizes a large amount of energy into this specific mode and thus allows the system to transverse that barrier, to overcome the bottleneck that makes going from A to B rare or occur on a characteristically long time. So especially if this barrier is much greater than kBt, I think we have intuition that the likelihood of seeing a trajectory that goes from A to B is unlikely. And what we're going to try to work through today is just how unlikely it is and with what rate it will occur. A consequence of a geometry to the free energy that is like this is that there is, in general, a separation of time scales between that waiting time, the time it takes on average to see a transition that goes from A to B, and the time it takes to transition. So if we were to actually plot dynamically what that trajectory looks like that starts in state A and goes to state B, well, if that barrier is large, much greater than kBt, we will see fluctuations about QA that persist for a long time. And only on characteristic timescales that are like 1 over the rate of that rare event will we see a transition. So if I was to really extend my axes here, maybe we would see another transition like so. So there exists, because of this instability at Q star, the fact that being at Q star is unstable, a little bit to the left or a little bit to the right, causes the system to fall down into a basin A or basin B, means that the time scale that the system spins intermediate between those two stable states is small. Let's call that time scale tau mole. It's a molecular time scale, some fundamental unit of time. And let's call the characteristic time it takes to see a transition, or the time between transitions, 1 over a rate to go from A to B. And we should expect that tau mole, for any free energy for which A and B are in fact metastable, for which there is a large barrier in between, that tau mole is much, much less than kBt or KAB. So this is what we mean by a rare event, and specifically a reaction being a rare event. It's not that a reaction takes a long time to occur because the atoms and molecules move slowly as they transition between A and B, but rather the probability that they do transition, probability per time that they transition, is small. But once they're getting ready to, the instability of the saddle point, or the barrier that sits between them, insists that they are not likely to live long at that transition state, to use some language that you are all probably familiar with. And thus, reactions are often referred to as fleeting. The time intermediate between A and B is small, even though the time to go from A to B is large. Okay, so let's actually understand these statements, now codified in a cartoon, with a little bit of mathematical rigor, to actually understand what we mean by a phenomenological rate constant, something that likely you've all taken for granted when you were first introduced to something like first order kinetics or chemical dynamics theories. A chemical reaction rate is something that you are often given, but not really asked to interrogate its microscopic or probabilistic meaning. And so that's the first topic on the agenda for today. And once we understand statistically what it means to define a rate, a phenomenological rate constant, we will be able to develop a theory for predicting it. And that theory specifically today will take the form of something known as transition state theory. First introduced a bit phenomenologically by Wigner and Irene, and all the way back in the early part of the 1900s, and has become a real important theoretical framework for thinking about reactive kinetics. Again, not only of real fundamentally chemical events like a bond breaking or bond making process, but the same basic ingredients goes into the estimation of a rate of a conformational change of a polymer or a phase change of a solution. Okay, so let's talk about some math. So let's actually take tau mole as a fundamental or basic unit of time. Again, it's the time it takes to, when primed, to go between A and B. It's the time it takes to actually traverse that barrier. So on average, if we wanted to see a barrier crossing, we have to wait some multiple of tau mole let's call the characteristic number of tau moles we need to wait N. N needs to be such that if I multiply it by F, the probability that I see a reaction occur that I see that fleeting excursion up the barrier, that probability, if this is a rare event, must be much less than 1. Given the probability is small, the number of attempts I need to wait in order to, with high likelihood, see a transition must be such that when I multiply N by F, I need something to be of order 1. I need that number to be of order 1. So if F is the probability that I see the transition, the time I need to wait in units of some basic molecular timescale, tau mole, in order to see a transition must be such that N times F is order 1. If we imagine that the system, as we've drawn in our cartoons, starts in basin A, the probability that it is still in basin A, given that the attempts are uncorrelated, is straightforward to work out. Let H a hat of T be the probability that the system starts in A and is still in A at time T, if F is the probability that I make a transition, then H a hat or bar of T must be equal to the probability that I did not make a transition, so 1 minus F. Time is measured in units of tau mole, and so up to T, or in multiples of tau mole, the likelihood that I am still in A must be 1 minus F to the N. Assuming transition attempts are uncorrelated. So the probability at each time that I make a transition is F, and thus the probability that I did not make a transition is 1 minus F. The probability that I am still in A given N attempts is just 1 minus F to the N. Now, if F is small, which we've assumed, which necessarily means that N is large, 1 minus F to the N is approximately E to the minus N times F, which is equal to E to the minus T times F over tau mole, which we can use to define a phenomenological rate constant, KAB. So out of a sequence of uncorrelated attempts, we find Poisson statistics, namely that the likelihood of leaving state A is exponentially distributed with a rate, KAB, which is nothing but the probability to make an attempt, to make a reaction, a probability to have a transition occur per unit time. So a first order reactive rate, reaction rate constant, has a statistical meaning, which is just the probability to make a transition per some unit of time, the time over which I can count an attempt as uncorrelated. Indeed, the connection to first order kinetics can be made explicit by taking the time derivative of HA that would be HA, still working with the bars, d dt is equal to, in this scaling limit of lots of attempts, minus KAB e to the minus t KAB, which is nothing but minus KAB HA bar is e to the minus t KAB. So I have HA bar on the right-hand side, which is indeed just the macroscopic law of first order kinetics. But now worked out in a probabilistic way, Ka being the probability to make a transition per time. Okay, so that is the object that we would wish to calculate in order to characterize some reaction, in order to characterize a rare event. We want to know the rate at which it occurs. So we've learned over the course of the semester that the relaxation from some non-equilibrium state, like being completely localized in A, is related to the spontaneous fluctuations of those dynamics about its equilibrium state. So if we want to understand how the system relaxes from HA, from basin A, there should exist a time correlation function evaluated in equilibrium that will characterize those fluctuations and thus encode the rate of a barrier crossing. Indeed, we can write such a correlation function down and argue that it's the correct one a posteriori. So let's consider an equilibrium time correlation function CAB, which is equal to HA at 0, some HB at t, divided by HA at 0. All right, so what are these HA and HBs? These are indicator functions. Specifically, HA at t is equal to 1 if, in our one-dimensional example, we are in HA. So let's call basin A, everything over to the left of Q star, and everything to the right, let's call state B. So this is an indicator that tells us whether or not we're in A or not. Its complement, HB, will be 1 if Q is greater than Q star and 0 else. And now note, in our one-dimensional example, HA plus HB is equal to 1. They cover the full space. As indicator functions, as binary variables, HA on average or HB on average has the interpretation as a probability. So CAB can be interpreted as the probability of being an HA at time 0 given, so CAB is a joint probability that I find the system in HA at 0 in basin B at t, divided by a marginal distribution, a marginal probability of being in HA at 0. A joint distribution divided by its marginal always has the interpretation as a conditional probability. In this case, it is the probability of being in B at time t, given the system was in A at time 0. And let's note that that is then the same as some complement function to our HA bar. This is HB bar at t. The probability that we end up in B at time t, given we started in A at 0. So let's try to understand the limits of this correlation function. It makes sense that it should be related to a rate because we're asking about how the probability in B builds up in time given the system starts in A. Okay, so what is CAB at time is equal to 0? So time is equal to 0. I'm averaging HA at 0 and HB at 0. The system cannot be in two places at once. It is either in the non-overlapping region A or its complement B. And so one of those is going to be a 1 and the other is going to multiply it by a 0. So the initial value of CAB must be 0. Essentially, by construction. All right, what about the long time limit? So as usual, if we assume that the system has a finite correlation time, if in long times the system forgets about its initial condition, I can average HA at 0 independently of HB at t. The HAs therefore cancel, and I'm left with just the probability of being in B, which is an equilibrium function in an equilibrium expectation value, which is thus stationary and thus independent of time. So it's just the probability of being in B. Now from the first order kinetics, macroscopic kinetics that we described earlier, we expect that the relaxation to this state to occur exponentially with some characteristic rate. So therefore, taking the derivative of this CAB, which is equal to this conditioned HB bar at t, should encode that rate. So if this is a rare event, we should expect, as argued from the cartoon, a separation of timescales between some fundamental molecular timescale and the rate at which a barrier crossing occurs. If we were to look at some time between those two tau mole and 1 over the rate constant, you might envision that the system reaches a steady state in which flux is continuously built, in which probability flux is continuously building up probability into the B basin. Indeed, since CAB is HB bar at t, taking the derivative of HB bar at t and evaluating this at 0 plus, so some time much less than 1 over KAB, but on the order of tau mole, given the complementary structure of HA and HB, that is the same as taking the time derivative of 1 minus HA bar at t, for which we worked out its time derivative here, evaluated at time is equal to 0, that evaluates that exponential to 1, I find I have minus KAB, I have a minus from this derivative, so that returns the rate constant KAB. So what we've just observed is that the rate constant, KAB, is related to the time derivative of this correlation function. When it's provided it's evaluated at some time, which is larger than a characteristic timescale for the correlation function to evolve, so that we don't just pick up its zero initial value, but short enough that it still is time dependent, so it has not relaxed completely to the equilibrium probability of just being in B. All right, so we have now argued, first by intuition and then by showing consistency, that there indeed exists a time correlation function for which its dynamics or its relaxation to its steady state encodes a phenomenological macroscopic rate constant for traditional first order kinetics. So if we were to plot CAB as a function of time, it's going to start at 0 at very long times that are like 1 over KAB. It's going to approach the equilibrium value of B, and it's going to do so exponentially. But intermediate, it's going to have some growth from which that rate of change will encode the macroscopic rate constant. The rate constant defined through a first order kinetics. All right, so then it behooves us to try to understand how we might compute that time derivative, how we might manipulate it in such a way so that we can actually extract from an understanding of microscopic dynamics some estimate of the rate of that rare event. So that takes us then to what is known as transition state theory. So a motivation for what we're going to do next is to note that while we have observed relationships between transport coefficients and integrals of time correlation functions, which are then easy to evaluate, there is a sense in which this relationship is similar and a sense in which it is going to be more complicated owing to the particulars of the process we're considering. So one could think about first order kinetics as an analogous transport equation. It tells you about how mass flows. Here, not in terms of place, from one place to another, but rather between one form and another. A goes to B rather than A flows from the left to the right. So macroscopic kinetics, like the diffusion equation, is a equation of motion for a density field. However, unlike the diffusion constant, which we know we can compute by simulating, say, a system of molecules as they move around, if we measured its velocity out, their velocity autocorrelation function, and integrated it, we would get the diffusion constant. That's a very viable way to extract a diffusion constant from a simulation. Or alternatively, to develop theories like our Langevin model to approximate that velocity autocorrelation function. Here, this correlation function, while also reflecting molecular dynamics, we know is going to be much more complicated to compute directly because its change occurs only through really rare fluctuations. To get a signal to be able to converge that time correlation function, we would need to see many transitions that takes the system from A to B and back again. That's what it would mean for that correlation function to actually equilibrate, is that I see so many transitions backwards and forwards that I lose track of where I started. And if the barrier is large, such that each one of those transitions is a rare event, that means we would need to spend an exponentially long time waiting around for a reactive event to occur, because by construction, we're looking at events that occur exponentially rarely with very small probability. So what we're going to do here is rewrite this correlation function in such a way that we shift some of the difficulty by applying a little bit of chemical intuition for what is causing this process to take so long, what is really gating the dynamics, which we've already kind of alluded to, the fact that reactive events are slow not because they move slowly, that the atoms and molecules take a long time to go from one configuration to another, but rather to do so requires undergoing a rare fluctuation. And it's just the likelihood of seeing that fluctuation, which is small and thus requires many attempts to be likely. So that's essentially the idea behind transition state theory, to try to rewrite this correlation function in such a way that we localize the smallness of the signal into a piece we know how to approximate. Okay, so specifically, we've just uncovered with this relationship that by taking the derivative of CAB, we can extract the rates. So let's actually take that expression and manipulate it. So KAB is a time derivative of CAB, putting in what we mean by CAB, the time dependence naively is in B. So CAB dot could be written as HA0 HB dot at T over HA of 0. For reasons that will be clear momentarily, it behooves us to actually move that time derivative over to the left. We know we can do that because this is an equilibrium correlation function. I could have written that numerator as HA of minus T, HB of 0, and took the time derivative on HA at the cost of a minus sign. And then I could move that time back. Alternatively, one could imagine opening up those angular brackets, acknowledging that that time derivative lives under an integral, and I could integrate by parts, assuming boundary terms are 0. Okay, so that tells us that the rate constant now has a slightly different interpretation. It is the rate of change of HA and how it is correlated with HB. So how does HA change? How do we actually evaluate HA dot? Well, HA is really a function of time through Q of t, through this reaction coordinate that defines the indicator function. So if I was going to take a derivative of HA with respect to time, what I really mean is that I want to know how HA changes with Q, and then how Q changes with time. So the rate of change of Q, well, that's some reaction coordinate. Maybe it is the bond distance between some dissociating bond, and thus I can attribute to Q a velocity that I'll just call Q dot. Now, HA, on the other hand, is a function defined on Q that changes from 1 for Q less than Q star discontinuously to 0 for Q is greater than Q star. The derivative then is 0 for all Q less than Q star and all Q greater than Q star, and divergent at exactly Q star. So the derivative of HA with respect to Q is finite only at Q star. So it's a delta function. And it's a delta function with a minus sign, owing to the fact that the step function is defined inverse to how it would canonically be. Okay, so putting that into our time correlation function derivative, we have CAB dot of t is equal to, we have a delta function of Q less Q star. We have a time derivative of velocity of Q at 0. Should also note that that was a delta function evaluated initially in Q. And then I have HB, also depends on Q, but a time t later. So I've got this delta function here, again, a binary variable, has an interpretation, if I average it by itself, of just the probability of Q being at Q star. So let's actually use that by multiplying top and bottom by that delta function on average. So now I have in the numerator the probability, an averaging operation, which is conditioned on being at Q star at 0, conditioned through that denominator, and being at HB at time t. I want to know, given those conditions, what is the flux, what is the rate of change of Q at time 0? So I could then rewrite that in the following way. This first term, the conditioned average, is the condition. So let's write this in two pieces. So if I took that piece in this denominator, that delta function in the numerator and the denominator performs a conditioning, makes this a conditioned average. It is the average of Q dot at 0, H, B at T, conditioned on being at Q star at time 0. So I average the flux at 0 and the probability of being in B, provided I start at the top of the barrier. So I've shifted my reference, not from just starting in HA, but rather from starting at the top of the barrier, accommodating some of that rareness, some of the high fluctuation, the rare fluctuation, understanding that that's what I'm waiting for. I moved that averaging operation, and thus my calculation of the rate, into a calculation that tells me that focuses on this bottleneck region, on this transition state. That can be seen even more clearly by looking at the leftover portions of that expression, a ratio of the delta function Q0 at Q star, that's the probability of being at Q star, divided by the probability of just being in A. And in an equilibrium, the probability of seeing a given configuration is just given by a Boltzmann distribution. So the probability of seeing Q star is just e to the minus beta omega of Q star. The probability of being in A is also just given by that Boltzmann factor, but now I need to integrate over all the different ways I can be in Q and also be in the region defined by A. These both have normalization constants, but those cancel. And thus I can write this whole thing as some Boltzmann factor for getting up to Q star divided by some measure, some quantification of the extent of that basin, which comes in through this volume element dq. So let's call that, imagining Q is actually a spatial coordinate, let's call it L. So putting this together, we have CAB time derivative of t is equal to a conditioned average of the flux of Q at 0, the probability of being in B at time t later, times the probability that I saw that rare fluctuation over some characteristic size of the basin A. This was exact. We made no approximations other than to say the system was evolving within an equilibrium. So we knew how to write down the probabilities of seeing specific states. This is a form of the rate constant of the correlation function known as the reactive flux correlation function. Flux due to the time derivative of Q, reactive because I start at the top of the barrier and insist that I reach state B at some time t later. So we've made our life easier by acknowledging that computing that correlation function directly would be cumbersome owing to the fact that it relaxes on timescales that are related to the rare event, which is unlikely to see happen at any point in time, using some intuition that what makes that reactive event rare is a fluctuation through a bottleneck, through a transition state, which is itself high in free energy, and thus very improbable to have occur. We absorbed that probability, the unlikely event, acknowledging the Boltzmann statistics for which the system is evolving and generating, and rewrote that rate as a product of some dynamics of flux and a correlation function between a flux and the likelihood of being in B given that flux. So all the dynamics of the system is here, and we've localized away some thermodynamics, encoding the probability of seeing this rare fluctuation. However, if we actually wanted to compute this, we'd still have to compute that correlation function in addition to knowing the free energetics for moving that particle along that reaction coordinate. So thus we need to evolve trajectories. We need to have a model for how those dynamics relax. Those are things we'll talk about in the next couple lectures. But for the time being, we can make an approximation. Again, here we've not made any approximations. This is an exact expression that tells us the linear response coefficient known as a reactive rate constant. But we could make an approximation that abstracts all of the dynamics away from this process. Let's do that by taking a short time limit. So let's approximate CAB at t by its value at time 0 plus. So we start at the top of the barrier and we don't integrate any dynamics. We just say that all of the important dynamical fluctuations are involved in getting the system to the top of the barrier. Once I get to the top of the barrier, I will neglect any subsequent dynamics. So what does that mean? The only time dependence is in that correlation function. If we evaluate this at time 0 plus, what happens? What sense can we make of it? So at strictly 0, a configurational variable like HB is independent of Q dot. So we should be able to average those separately. And moreover, the only way to get a finite, HB is only 1 if the system is in B. The only way to have the system be in B at time 0 plus is if it was going that direction at the top of the barrier. So that means we only want the positive velocities that we've averaged. And given we have a positive velocity at time 0 plus, all of those positive velocities we envision will react. So one way to average Q dot and ensure we have only the positive velocities is to acknowledge that equilibrium statistics dictates Q dot is an even variable. And so I can average its absolute value and multiply by a factor of 1/2. Now note, again, because of the uncorrelated nature of velocities and configurations, true classically, the average velocity is independent of the configuration I'm evaluating it in. So that conditioning also goes away. So again, to say the only way HB at 0 plus is 1 is if Q dot at 0 were greater than 0. And thus I just need to average Q dot given it's going in the positive direction, or 1/2 its absolute value. Inserting this back into the correlation function, I have CAB dot at 0 plus is equal to 1 over 2L, L being the extent of that A basin, the average Q dot, and now the probability to get to the top of the barrier. And this is, in fact, what is known as the transition state theory estimate of the rate. It's a quantity that is purely thermodynamic. We know the average thermal velocity from that second term on the right-hand side. And we need it times the probability of having a fluctuation that takes the system from a well, a basin A with width L to the top of a barrier. And thus that's what we wait on when we wait to have a reaction occur. So a rate, the probability per time of seeing a reactive event, is determined completely by the probability to get to the top of the barrier times the flux over that barrier. And specifically, transition state theory approximates that flux just by its thermal value. So this approximation, if I wrote e to the minus beta delta E in the argument of that exponential and said that the rate was proportional to an exponential of a change in an energy, that would be called the Arrhenius form. Arrhenius stumbled upon that by mapping out a bunch of different gas phase experiments. Theoretically, this was first motivated by Irene and Eugene Wigner, both at Princeton at the time. Irene being in the chemistry department thinking about actual molecular processes, Irene thinking about approximate dynamics, quantum dynamically, approximate theories of quantum dynamics. And it really serves as the bedrock for most of the thinking behind reactions. Namely that the first order thing one does if you want to estimate the rate of a rare event is to intuit a scale of a barrier, or to compute, if one wants to make it a little bit more quantitative, a barrier height that has to be overcome. The exponential of that barrier height then gives you, within prefactors, the rate of that rare event. Indeed, it's pretty remarkable in its scope and how well it works. Essentially, on the exponential scale over which linear changes in free energies affect changes in the rate, transition state theory is incredibly accurate. As long as you have a good idea of a reaction coordinate, where to draw this dividing surface, this Q star that separates reactants from products, you can make a reasonable estimate. But it is an approximation, and so it behooves us to understand exactly what that approximation is. So what have we thrown out by taking this short time limit? And when can thus transition state theory really go awry? Well, if we were to plot this free energy surface, we've just estimated the rate of that event by envisioning we start at the top of the barrier and we consider systems which have positive flux at time 0, such that they end up in B. Now, what could potentially happen? Well, imagine, for example, that this Q coordinate is only one of the coordinates in the system, that there were dynamically other coordinates that were important. Say, for example, this Q is a bond length, but that bond is a bond of a molecule in a solution. It's entirely imaginable that even though I start initially with some positive velocity, that in moving to the right, the bath could hit me and cause me to turn around. If it does so in a way that takes out enough energy, I could fall back into A. That is a contribution that we've neglected, a recrossing event that even though I start going in the right direction, I could end up going in the wrong direction. And thus I would have overcounted the flux, because that trajectory, the red one that I've drawn there, would have given me HB of 0, and thus should not have been included in the estimate of the rate. It added up too much flux than should actually have been counted. Analogously, I could have envisioned the complement. Imagine, for example, a trajectory which was not included, a trajectory which had an initial flux in the wrong direction, but got turned around by a bath fluctuation, say, that enabled it to react. This too leads to an overestimate of the rate because the initial flux Q0 I've overestimated by ignoring negative contributions that should have indeed been averaged as well. So the negative velocity that would have entered into that correlation function has been neglected. So indeed, one can define a so-called transmission coefficient, kappa of t, as the ratio of the full time correlation function, CAB dot, to its zero value. And this ratio is strictly bounded by 1, implying that transition state theory is strictly an upper bound on the rate. Or a correction to transition state theory includes those recrossing events that serve to reduce the rate below its transition state theory estimate. So again, transition state theory acts as an upper bound because it neglects these recrossing events by approximating the flux just by its zero value, that both act to suppress the rate, either by averaging negative components to the velocity or by averaging zeros in the indicator function. And a correction to transition state theory can be constructed by computing the so-called transmission coefficient, which, if one could compute exactly, would give rise to the exact rate in a two-step procedure whereby one first computed the transition state theory estimate and then the transmission coefficient. So in the next couple lectures, we'll actually talk about theories of this transmission coefficient, first by Kramers, then by Grote and Hines, which build in some other physics through different approximations to the dynamics. Because again, that transmission coefficient is where all the important or non-trivial dynamical information resides, because it is the portion of this rate which derives from a time correlation function. Okay, so to end today, let's actually just work out a concrete example where we can compute some of the integrals exactly to give you a feeling for what transition state theory looks like. And let's work out a case where everything is locally harmonic. So let's imagine, for example, that we have this free energy profile, omega of Q, which is locally harmonic about basin A, and locally harmonic around the barrier. Such that near the barrier, omega of Q is, to a good approximation, 1/2 m some characteristic frequency, omega B squared, Q less Q star squared, plus some offset, delta omega of Q star. Whoop. And let, in the vicinity of the basin A, let's assume that omega of Q is well approximated by another harmonic function with some different characteristic frequency, Q less QA squared. So in such a case, what would transition state theory give as the rate? Well, to compute transition state theory, we need to know a couple integrals. We need to compute the average flux. We need to compute this L, which is an integral over basin A, and we need to know that offset. So most simply, the average flux, absolute value of Q dot, thermally averaged divided by 1/2, is just an integral over Q dot, weighted by a Maxwell-Boltzmann distribution, like so, normalized, like that. Absolute value can be turned, times 1/2 could be turned into an integral over the positive domain of Q dot. That's an integral that we can do and would give us 1/2 pi beta m under a square root. Similarly, L can be evaluated as an integral from -infinity to Q star over the configuration Q and its Boltzmann weight, e to the minus beta m omega naught squared Q squared. Having shifted it away from QA, as long as QA, as long as this rise in the probability is large by the time it, well before it has gotten to Q star, doesn't really matter where it's centered at. That integral, another Gaussian integral, we have done many of those recently, but that's one we all probably remember. It will give us 2 pi beta m omega naught squared, square root of. All right, so putting that all together, we have KAB, transition state estimate. We have a Q dot, which gives us this. we have a divided by L, which gives us that, and the probability of getting to the top of the barrier, e to the minus beta delta omega. So 2 pi and 2 pi under the square root will give us something under 2 pi. The beta m's cancel, and omega naught squared under the square root comes upstairs omega naught, giving us this. So the transition state theory estimate of a rate, provided all of the features on the potential are locally harmonic, is just the characteristic frequency of the well. That tells you the fundamental time scale over which attempts to overcome the barrier are made. They happen every omega, or with a characteristic time of 2 pi over omega. And the rate is then the probability, the frequency of those attempts times the probability that the attempt got you to the bottleneck stage, exhibited the rare fluctuation that took it all the way to the top of the barrier, in this case, encoded by delta omega as the barrier height. Okay, so that's all I really have to say today. We've turned our attention to rare reactive events and found a relationship between equilibrium fluctuations and macroscopic rate constants, which encode the probability per time for a rare event to occur. And we have, by manipulating that correlation function, using some physical insight as to what makes a rare event rare, a rate occur on a long characteristic time scale, namely that what we wait for is not just the slow motion of molecules, but rather a rare fluctuation that overcomes a bottleneck that passes through a transition state. We're able to manipulate the correlation function to arrive at transition state theory, provided an approximation that we throw out the potentially important time correlations, the dynamics at the top of a barrier. And what we get, though, is something pretty spectacular, a purely thermodynamic relationship encoded in free energies and thermal fluxes for the rate of some rare event, which is used ubiquitously across physical sciences. In the next couple lectures, as I've alluded to, we'll relax that restriction, that approximation, by working directly with that transmission coefficient and trying to figure out ways to approximate it. So stay tuned for that, and I'll look forward to seeing you all in the small group discussions this week.